well, number one, it's distracting, but number two, we're recording all of these professionally, and they're all available to you as soon as the trade show is over. So you have access to the slides and the presentation at any time after the end of this week. So if you could please try to honor that request, we appreciate it. And as far as surveys go at the end of this presentation, the QR code's on the wall. If you take a picture of that and fill out your survey that way, once you pull that up, you get the opportunity to pick the session. So you can do this session if you forgot some earlier today, or if you're going to take some follow some presentations tomorrow, you can use that same QR code. Every time you fill out a survey, you're entered into a drawing for a $100 Amazon gift card. And we appreciate that feedback because that helps us when we are curating the technical sessions for the next FNA. Now we'll move on to our presentation. Mr. Robert Sanderson will help us learn the valve train fundamentals, field strain components, valve proofing systems, and more. We'll learn about press indicators, control valves, and grasp pressure drop essentials. So please help me welcome our speaker today, Mr. Robert Sanderson.
Thank you. I want to start a little bit, first of all, saying that I'm not a slide reader, so there'll be stuff up there, but I tend to add a lot of commentary to what's on there. I figure everyone can read by now and pick up all those points. The second is that, excuse me for coughing a bit. 2 weeks ago, it was either COVID or Ebola, one of the two, and I'm still getting a little bit past it. I'm not contagious anymore, so everyone in the front row, you're fine. But I do have a tickle in my throat, so sorry about that. Valve trains. They're not necessarily glorious. It's not the first thing you think about when you're putting something into a heat treating shop. Everyone focuses on the burner and getting the burner sized and put in there correctly and all that. But really the performance of the burner is governed by the controls and the valve train. The burner is a fantastic mixing mechanism. You're picking it for the right shape, the right emissions, the right performance you want. But how it performs is really completely dependent upon the controls that it's hooked up to. The burner doesn't go to high and low fire. The valve train controls it. Your systems are watching over everything that's operating in there. And so understanding this hidden gem in the background is very important to making your system operate properly. I like to make it somewhat of a similar comparison to putting out a dragster out there. You got a fantastic motor to put out a lot of power, but it's the transmission that makes that go or idle along. You can't mow your lawn with a dragster because it doesn't go that slow. So you've got to have everything sized right for the high performance as well as the turn down operations, and then all the safety functions in between. And this is what I want to go through a little bit with the presentation. So we're all somewhat familiar with valve trains, a lot of different shapes, sizes. They're all process dependent upon what you're doing. Valve trains are common for fuel, but they're also used a lot for compressed air, oxygen, various metering systems, nitrogen. There's a lot of different systems that are out there, but they've got some fundamentals on their basic systems. On a fuel train, a fuel valve train, the heart of the valve train are the safety valves. They have to remain closed at all times, and they're only ever allowed to open once 100% of everything else is proven okay. We'll get through some of that a little bit later on. Then you've got a number of devices beyond that for control, regulation, metering, filtering, just to maintain everything, to make sure everything is operating in a safe and controlled manner. So early on when we're starting with this, someone needs to make a control diagram on what needs to be put into the system. There are a number of schemes that are used. There's ISA, there's ISO, and there's some other P&I instrumentation systems that are done for it. Sometimes people put flow numbers on them as well. Then it's a bit of a process flow drawing. But it's good to put that up front to help you work through all the different elements you need on there, because different applications have different valve needs, different location needs, different code needs, and it's good to put all that on there to keep everyone start talking and understanding the arrangement. And once you have that down, then you can start getting into sizing and selecting and figuring out the performances on the different elements. So the engineers will come up with a variety of schemes and put something out. And this is just a sample of a rather basic process instrumentation drawing. I like Excel, so you see a lot of Excel things that are on there. The typical components we'll go through, there's up to around 20 different items that are on a valve train, and they range from mandatory items to features that are sometimes necessary, and others that are just some nice useful options to have. And these are all based on the predominant code I'm going to be talking about, speaking to, is the NFPA 86 requirement. There are a few others in NFPA world, 85 and 87, which cover boilers and thermal fluid heaters, and 86 pretty much covers everything else. It's called ovens and furnaces, but in reality, it's any combustion equipment. Those terms are used synonymously, so it can be for air houses, it could be for bread baking, it could be for high-temp furnaces, thermal oxidizers. It's all part and parcel of the same thing, as long as it's not a boiler, not a thermal fluid heater. There's some subtle control differences in those other systems. So the items that are highlighted with the explanation points, those are items that are necessary per NFPA 86. Items with the green dots are items that are sometimes required by your insurance requirements or your process requirements, but they're not strictly required for NFPA. And then the mechanics tools are some useful items. I do recommend people put them in, but they're not always necessary. And you'll see some items have two different demarcations on them, and I'll explain why there's two on them as we get through the slides. We'll have plenty of time to talk about this. I've got you for the next 2.5 hours, they told me, so we're good. Valves, I'm going to start with manual valves. It's the beginning of the train, even though the safety valves are the main one, but we'll build on the basics here. Manual valves they come in a variety of different shapes and sizes and purposes. Most of the manual valves out there are used for an immediate isolation or a positive isolation, so it's a simple quarter turn device. There's typically a handle that are on them, and the handles, when they are used for isolation, need to be oriented such that they indicate whether the valve is open or closed, and you can see based on that handle orientation. Sometimes they have locking mechanisms. This one has a locking mechanism based on the handle orientations. The locks can be made so they can be locked open or closed, closed only, open only. It depends on the process and the way you're using them. There's also lubricated plug cocks, and those are also for a positive isolation. And then there's other varieties which are put in, such as needle valves, control valves, different process valves. But the common thing that all valves have is that all valves leak. All valves, all leak, always. And I'll make that simple assertion that we could start with your simple, go into your bathroom and go to the faucet there, you get a sap of water, brush your teeth, that valve leaks. Your cold water valve leaks. The question is, how much does it leak and how much of a nuisance is it? Does it drip once every 10 years? Once a year? Once a month? Once a week? Once a day? Once an hour? How quickly does it need to escalate so that you need to decide when to handle it? So the safety on the valve trains is built around the assumption that all valves all leak, and you have to put precautions in to watch for that. All valves leak because they have seats and stems. So they're not going to, if you close the valve, it's not necessarily going to go through the metal, but it's going to go around the openings, through the seats, through the valves, through the stems, because things get worn out with time. I say on burners, but also on valve trains typically, the top 3 reasons for equipment failure are dirt, dirt, and dirt. They get into grit. Grit gets into equipment, grinds it out, wears it out. Once you start having a channel going, then you start getting erosion. Erosion is just a high velocity stream that has some type of dirt or grit that's in it, and it starts pinholing and creating bigger openings and bigger leaks. Packings get loose because they get dirty and they get things that are into them, so they're a service item. So they can leak around, and they can also leak up through and around the stems, different areas. So having a high quality valve is something to look out for and keep them going. All the modern codes allow and actually prefer you to use ball valves with Teflon stems and everything on them, but you can use lubricated plug cocks, which are shown down here. Lubricated plug cocks are the industry standard, and I like to say it's the best technology 1950 had to offer. There's a lot of advancement since then. People often say, well, they need to grease the lubricated plug cock once in a while. That's a bit of a misnomer. It's not actually grease that you're putting in. People, it is. It looks like it. It looks like you're using a grease gun. It's actually a sealant that you're putting in there. And you're putting sealant in, and it's built with special ports such that when you attach the sealant gun at the top, and you inject the sealant, it goes down the board stem, fills the holes, and actually lifts that lubricated plug cock into position and adds extra sealant around the edges. And it's the quantity of that sealant in the valve body which prevents fuel from leaking through and around it when it's in the closed position. But over time, the pressure pushes and squeezes that excess sealant out. Sometimes it'll evaporate, it's temperature sensitive, it may be media sensitive, and it gets through and away, gets all liquidy, flows out, and you have to go back and service them annually to make sure that things are working, and operate them to make sure that they don't corrode into place. Nothing worse than having to close that valve and finding out it will not move because it's frozen in place. So starting there, everything is building on the basic valve technology. Sediment traps. Sediment traps are typically put in right at the beginning of the train, downstream of the very first isolation valve. And they pick up the big globs, sediments, drops, big items that pass through the valve train. They're not meant to pick up all the fines. They're meant to pick up all the large debris and liquids that are in the gas line. Well, what liquids are in the gas lines? Well, you'd be surprised. There's actually quite a bit of water in gas lines, especially the further south you head. Head further north into Canada, the gases are very dry. They run them down to a dew point of negative 40, negative 30 Fahrenheit, Celsius. They get real cold, dry all that out. As you head further south and get into areas of Texas especially, they don't dry them quite as well. It's quite common to have dew points which are only 30 or sometimes even 20 degrees. So when you get a really cold snap, such as has been happening down in Texas a couple of days, it's not unusual to suddenly find all those little bits of water vapor have crystallized and frozen up and locked up all the safety equipment and the regulators and everything. And they can't, you need to get the heat on, but you can't get it on because the valve is literally frozen in place. So sediment traps are important. When it gets cold, that water will have to go somewhere, and there's a good drain down here for it. And I think the batteries are getting a little weak. I think part of the reason, too, early on for the sediment traps were that lubricated plug cocks in the 50s were the best way to do it. And Fred, the maintenance guy, would go out there and he'd hook the ratchet up and he'd give it 10, 15, 30 pumps is good. It needs 2, but 30 is better. All that excess sealant has to go somewhere. And it would accumulate and fall into the bottom of these sediment traps. I pulled a lot of sediment traps off over the years. Sealant is a common one with lubricated plug cocks. I found welding rod, birds' nests, birds, a lot of different things in there, especially on brand new facilities. Yeah, so it is a necessary thing. And there is a proper orientation for sediment traps. You want to feed down in and then turn 90 degrees to come out. So that way any contained debris is carrying the momentum and it hits that turn, and the momentum keeps the gas going forward. The gas will turn because it's a very light molecule, but any debris, large debris, will just fall out and accumulate into your sediment traps. Downstream of the sediment trap is a finer mesh strainer. There's no real published standard on strainers. If you're not paying attention and you just buy a strainer and you put it in, you're probably going to end up accidentally buying a steam strainer. So they're going to give you a number 40 mesh, and they're going to give you a cork gasket around where the filter is there, and you're going to be fine and happy until one day it just quits working. A 40 mesh strainer is not really going to pick out a lot. Pretty much anything that would have fallen out in the sediment trap is the only thing that will pick up, but the sediment trap has picked everything up. So it's just going to let all the smaller debris pass through to the finer elements downstream. You're trying to protect your orifices, you're trying to protect your regulators, you're trying to protect your fine equipment downstream, and a large mesh such as a 40 is not going to work. Additionally, the cork gasket is not going to last all that long. Cork is a porous material, it's a natural material, and the gas may be contained initially, but as you run longer, that cork will naturally dry out, become brittle, lose its elasticity, and it will no longer seal that seat on there. So it should be a fuel-rated seat for what you have on there. Cork is fantastic for steam. It's economical, but it's not properly rated for fuel. So typically a Buna or a Viton or some other type of softer elastomer will work. I personally, on the mesh sizes, I like to run to at least an 80, but I prefer a 100 mesh screen on there. 100 mesh screen pulls out a lot of materials. And I've got a rule of thumb on there for the constant 120. What kind of mesh versus micron? Rule of thumb, 120 mesh is roughly 120 microns. And as you start getting smaller on the mesh, you can hold as a constant. So 150 mesh is 100 micron. 100 mesh is 150 micron. They kind of roughly work back and forth that way. There are some conversions that are in there. And the way to determine a mesh, if you're really not certain, you have to have patience, but the mesh size are the number of holes per linear inch. So you get a ruler up there and you count the number of openings per linear inch, and that's what you have. 40 seems like a lot of holes, but they're actually quite large when you look at it. You can pass a lot through there. 100 mesh will stop right about the size of a human hair on edge as it's coming through. So if there's eyelashes in the pipe, so to speak, it's not going to catch that. But it's also going to pick up the fine dust, which naturally does occur as pipe systems age and start sending that dust through the lines. And that will protect your downstream sensitive equipment. A couple slides on regulators. People like to think that regulators control flow, and they do not control flow. They control pressure. They measure the pressure at the outlet of the regulator, essentially, and try and maintain that. The pressure at the outlet of the regulator is a function of all the downstream resistances. So that's all it's doing. So it accommodates the chamber pressure, the burner resistance, the valves, the safety valves, control valves, any other orifices, flow metering, anything that's downstream of that. That's all part of one big system calculation, generates a back pressure. It's really no different than if you're sizing a fan. The fan is developing a pressure, and the pressure at the outlet is related to how much back pressure the system has. You have to work backwards relative to your flow. Lots of different styles of regulators, direct, levered, and balancing. We'll get through those in the next few slides here. But whenever you're picking a regulator, which is right at the heart of the system, people want to size a regulator first. It's about the last thing you can size, unfortunately. You need to know more than just the fuel type, max and min flows, because you're trying to say, I need to get at least this much, but I need to control down to this bottom end. You need to know the inlet and the outlet pressures, as well as where they could go. How high could it go? How low can it go? Where do I need to be? Just so you have some control on the tolerances. And there's a lot of different specialized features you can have. Make a whole nother presentation on regulators here, but I'm not going to. But there's some common ones to put in there, such as OPCO and UPCO, overpressure cutoff, underpressure cutoff. Those are an additional safety feature on the regulators. Typically, it's a device which throws a cork into the pipe at the beginning in case there's a problem. Regulators typically fail open, which means if they break, they send the full line pressure downstream. An overpressure cutoff will detect that and shut it off. And underpressure cutoff will detect a high flow lack of back pressure. That could happen if there were a line break, if there were an open valve into a room in a piping system, a fork truck hits something downstream and breaks the pipe open. That's when you'd have an underpressure cutoff. Those are the most common safety features. And lockup is one that I will talk about as an important feature too, as a positive lockup. You assume the regulator, when there's no demand, is going to go closed. But what if it doesn't go closed? What if it doesn't quite shut bubble tight? Just like that faucet, it drip, 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 drip. That pressure will, those drips will accumulate and develop a higher pressure downstream against closed valves. So that's the type of lockup you need to understand. Is it a bubble tight lockup? What is it? What does it do? Not all regulators are positive lockup. And I've got the two symbols on here. It's mandatory, but it's also a nice feature to have if you need it. NFPA doesn't require you to have a regulator in the system. It only requires you to have a regulator if your downstream system cannot perform without one. If it's not safe to have a high pressure excursion coming in. So if you have a very low building pressure, let's say a half a pound, you don't necessarily need to have a regulator at all if your equipment is basically sized to run at a half a pound, because you can't have that overpressure emergency. But if you've got 50 pounds outside and you need a half a pound in, then you need to have a regulator. Regulators start with the most basic function, which is a direct acting. Everything is in line. Then for additional turn down, they go to a lever acting design. And then once they get above that, where they need higher and higher turn down, they get to a balanced design. The first two regulators have three forces that are working on them: an inlet pressure in red, an outlet pressure in blue, and an atmosphere spring pressure in yellow. Those three are in tandem. It's like having a teeter-totter on your playground. You got a large kid on one side, a small kid on the other, and you move that teeter-totter left or right on the balance beam until everything is level. But what if one of those three things changes? Well, then the teeter-totter has to move. Well, when could that possibly happen? Oh, I don't know. You start the furnace up, you get it all commissioned in the middle of summer, you got lots of gas pressure outside, everything is fine. In the middle of February, you can't get heat anymore. Well, it's because the street pressure has dropped off. Everyone in the neighborhood has turned on all their furnaces and all their heating equipment to heat up their buildings, and it's dropped the street pressure. And so you've only got three forces. You lost inlet pressure, you can't change the spring, so you're going to lose outlet pressure. And you see it for a lack of furnace condition. Or the opposite. You start in February, and then in the middle of summer, you're just too hot. You can't get turned down on the equipment. Same reason. Now your street pressure's gone up, so it's now pushing more gas pressure out. So a direct acting regulator, we'll start with this first, and then we'll get on to that balanced one. The stem and spring are in line. It's one direct line system on there. Typically that type of system that regulator is typically listed for about a 40-to-1 control range. So if your equipment is operating inside that 40-to-1 range, it's going to give you the proper high and low fire conditional flow. But if you don't land exactly in there, or you have a much higher turn down, an 80-to-1 turn down, you need to get to a different type of regulator. And that's where a lever acting regulator is put in. So now there's just another interposing mechanism between the two, which adds some fine-tuned capabilities in there and allows you to get a finer turn down, roughly 100-to-1 turn down flow. Both of these styles typically are involved with what's called droop, which is that summer to fall heating system I was explaining a little bit. They're limited at the bottom end because they're worried about that inlet pressure varying a little bit and you're losing control, so you tend to oversize those regulators to help compensate. A balancing regulator is one that goes an extra part and it has a fourth force in there, and there's an additional specialized spring cartridge inside the throat of the regulator. So now if the inlet pressure varies, the spring cartridge reacts and you hold the same outlet pressure. So it's more stable across all the operating conditions, and typically with that type of a regulator you can get upwards of a 500-to-1 turn down. The turn down is really the finesse on how low you can go at the bottom end. And for pilots you need very low flow, typically well over 100-to-1 turn down. So typically on a pilot line you'll end up with an independent regulator. But if you do it right with the balancing regulator, you don't need to, because you'll have that turn down capability all built into one system. Relief valve is a twist that is on the regulator. It's basically a regulator that's used in reverse, a simple way to think about it. It's hooked up to the line. If there's way too much line pressure into the system, it will react and actually pop open. It's the overpressure relief. Pops open, and then it runs off to a safety vent location. But internally, it's built the same as a direct acting regulator. It's just the way the sensing mechanism is ported internally that allows it to relieve when there's a higher inlet pressure. Otherwise, it is closed. This is the closed position. This is not shown in the venting position. Pressure switches are related to regulators because regulators can typically fail in one of two positions. They either fail open or fail closed. Most of them fail open, so we have a high pressure switch. It checks for the alarms, the overpressure condition. A low pressure switch in industrial code is necessary to prevent you from starting up equipment and the event you have a lack of pressure. It's more of a nuisance alarm, but on larger and larger systems, it also prevents you from trying to light something repeatedly when you just don't have the adequate fuel supply to make that happen. Some codes, not NFPA codes, but like for your HVAC codes, your ANSI Z codes, do not require low gas pressure switches. Your home furnace is a small BTU unit. It does not have a low gas pressure switch. It has a high gas built into it, but not an under minimum. It just doesn't light if it doesn't have the gas. Lots of different varieties out there. Used to be you had to have lights to indicate the position on them, but that's been taken out of the codes now. Lights are a nice operating function, but you can put lights in. They can be open for running or open for fault. I should say on for running or on for fault, however you want to wire them up. It's entirely up to you, but that's the way they go. Safety shutoff valves. Everything we've done is to watch and to protect these major systems here, the safety shutoff valves. They come in a wide variety: manual, automatic, electronic, pneumatic, hydraulic. Once upon a time, again, best 1950s technology there was nothing but manual Loctite valves, manual throw switch valves, dead man switches they're typically called, because the flame safety systems couldn't handle the current inrush to open these things. So typically the safety systems would just look for the safety conditions and release them to close automatically because they are fail-safe closed devices, and would require the operators to go out and throw the manual switches to open them. There's no requirement for that these days now. Many controllers now can handle the inrushes, and the inrushes have gotten lower and lower as with other electronics advances. But part of the 1940s, 1950s heyday was they wanted the manual switches on there because they wanted the maintenance guys, the operators, to go out and physically walk around the equipment and look, sniff, breathe, eyeball everything, make sure everything was normal, and then throw those switches to open them and operate. Not so much today. Today it's equally safe to operate everything automatically. So there's a lot of variety out there. Electronic valves are typically the ones that are used up to around 3 or 4 inches in pipe size. When you get above that in pipe size, there's often too much current, too much time, too large of a valve to have to open and close, and so they'll often switch on the larger valves, although they're available in smaller ones, to the pneumatic systems down at the end. The pneumatic systems, again, have springs in the end. They fail closed, a ball valve which rotates very fast in there, and there's a solenoid on the side which drives the air cylinders. So you're still actuating a very small current. They're also very good in incentive atmospheres because you can use a DC current on them, and everything is non-sparking, non-arcing.
So are those essentially ball valves? Are they gate valves?
Typically, these are fast-closing ball valves, spring-operated ball valves. And the trick isn't the spring to close the valve. That's pretty easy to do. The trick is stopping the motion, not slamming through the end stops and having it spin off like a top. That's really where the fault is. It's on those things. They're also very good for much higher pressures. Probably some of the highest pressure systems out there will use those a ball-type valve, because you can get some of those into the thousands of PSI for the rating capabilities on them. Vent valves are the functional opposite of a safety valve. These are fail-open devices. This came with the advent of boiler codes, closed chamber codes, and an insurance underwriter at the time called Industrial Risk Insurers, sometimes known as IRI. They're not around anymore, but the name is still out there. I need an IRI system, or a double block and bleed system, and they're a vent valve. Recognizing that all valves all leak, if you just have two safety valves in series, and the first one leaks and you're off for a long time and it leaks bubbles through, it's going to push all that pressure against the second valve, which again, all valves all leak, and eventually that pushes through into the chamber. Boilers present a particular hazard on that, in that once it leaks into the chamber, it's in a closed, confined space, and people have to be very careful about how to make all that go. So the thought behind a double block and bleed is that between these two valves, a vent pipe is added, and that valve fails in the open position and is energized to close for running, and it's interlocked in the closed position or the open position, so you can see how everything is running. So the theory being is that if the first valve leaks, it pressurizes forward into a 0 atmosphere chamber and has to naturally rise out and cannot squeeze any of those gas molecules to the downstream chamber. The problem, however, is if that downstream valve, if it has a positive back pressure, it can push backwards against that valve, and so that second valve needs to be rated for both positive pressure as well as negative back pressure if your system's under a high chamber condition. So you need to be careful on how those are running. There's a lot of equipment with vents. A lot of equipment is vented improperly. This is a sample of what was obviously an improperly vented regulator, what's left of it. It was not vented at all. They said I didn't need to put a vent in, I'm in a good area, and it failed. The diaphragm ruptured open, it vented out, blew the gas across the local electrical junction NEMA 12 box, found a sparking point, and came back and took out the regulator. And then the excitement happened after that. So, lots of different vents that are out there. Vents are typically put in for 3 reasons. One is, I mentioned the double block and bleed as an atmospheric vent. That should be vented by itself. Others are because they're devices that need reference points, and items that need reference points are regulators and pressure switches. They have diaphragms in them that move, and they need something to be back pressured off of. If they can't go to the chamber, then they should be vented to atmosphere. But the vent sizes just need to have a connection going all the way through because it's not normally moving volumes of fuel through it. And then you have a relief vent. That was early on, I showed that pressure relief valve. That is a safety device. That one does need to be sized carefully. So when that relief valve goes, or if this regulator had an internal relief on it, you need to watch the piping sizes. Look at how many pipe feet there are going out, do the back calculations, add the screen, back pressures, and watch how all that goes so that if it vents properly, adequately, and not too small. If a safety vent is undersized, it won't relieve, and it will allow the fuel escaping through the regulator and push it downstream through the valves. So all that needs to be watched over. Many useful options: valve proving systems, test port fittings, and pressure indicators. Combination of mandatory and useful items. Valve proving systems are optional devices. They're useful items, and they will provide, depending how they're set up, at the beginning of the startup, at the end of a shutdown, or both, depending on how you've got it programmed, will do a cycle test or a pressure test on the safety valves to ensure that they are shut. So they can replace, if it's in North America, if it's allowable to the insurance underwriters, they can replace a proof of closure system. Proof of closure systems are only really viewed in North America. If you get outside of North America to Europe or other areas, they require a valve proving system instead. So a valve proving system will show you that the valves are shut, just like a proof of closure. Neither a proof of closure nor a valve proving system will prove that the valve is bubble tight shut. It just proves that it's not leaking horrendously. It's shut enough that it can pass the test. But it does not replace an annual safety bubble test to ensure that the valves are holding up to their conditions. Test port fittings are useful devices. Test port fittings are optional. Test ports are mandatory. To me, I like to always put test port fittings in. They're cheap, they need to be put in, but everyone tries to be cost effective, and so they won't put them in. But if you need to do when you go to do your annual leak tests, if all you see is a tap on the side of the train, it's a lot harder to start getting into. You need to bring the fittings, you need to put them all in, make sure all those aren't leaking, bubble test that. I mean, they're nice little devices to have, and when you have a problem, again, it's a lot easier to have that to quickly check something out. Same thing with pressure gauges. Instrumentation is nice, but instrumentation is not mandatory. It's there for your service and your maintenance. Control valves are optional. They're very handy to have. Not all burners have them. If you're pulse firing, you probably don't. You've got a manual valve that are setting it. But if you have a modulating valve, the control valve is one of the key items to performance. A lot of people just throw the largest valve they can, and that is wrong. That is oversized. Really what you need to do is you need to size the valve not just for the full open, but for the minimum flow, because your turn down on your burner is going to be ultimately determined by your control valve. If your pressure system is set up and you've got a large, let's say a 30 inches of pressure drop on everything except for this valve when it's wide open, it's got no pressure drop, 30 inches and everything else. But if it's oversized and closed and can't hold back, when you go to low fire, you've got no downstream pressure. It has to hold all 30 inches back. And if it's oversized, it's got too much leakage around the perimeter. It won't do it. So you've got to watch both ends on that. This is the key to performance. And if you've got a variety of fuels or one linkage item, you may have a number of them in there because every valve, when it moves, has a different characteristic. In this setup here, you've got an actuator or a manual device, and all you can really do is open and close the air valve, and then you have to tune the gas and the oil by setting the little linkage pins that are inside the cams to get them tweaked so that you're flowing in correct proportions to hold your burner on flame, to hold your emissions, to hold your proper air-fuel ratios, keep everything moving the right way. So I talked about the importance of sizing control valves. It's all about pressure drop for making things go. Pressure drops are compared by a CV factor. And I've got an equation up there for working things out for the pressure drop. So those of you who are math nerds such as myself, you can just copy this information and start working through it. Some of the information, especially if it comes out of Europe, will be listed as kV. kV is also similar to CV. There's a conversion constant. It's just that it's based instead of gallons per minute of theoretical water. It's based on cubic meters per hour. For low pressure systems, meaning burners that are running at under a pound, I like to recommend people use a 4-1-1 system for sizing equipment. Allow 4 parts of the pressure drop to be the burner, 1 for all your piping losses, and 1 for your control valve. That will get you into a relatively good initial control size. Your engineers can really fine tune it from there because nothing is ever going to perfectly fit those numbers, but it gets you into a starting point. So, almost done. Some sizing rule of thumbs. On sizing your system, you have to start at the end of the pipe. Everyone wants to jump to the front, size the regulator. The regulator's the last thing you can do. You got to start at the end of the pipe. So your chamber pressure, and work yourself backwards all the way through, all your items as you're coming backwards. After you know that, then you can hone in again and resize for the control valve that you need to make sure things are going. Then you can size additional ancillary devices, orifices, pressure drops, take into account metering plates if you need them, any specialized bits, and put everything in. A lot of stuff is tabled. You can work off values and do extrapolation, or you can go back to first principles and calculate the pressure drops. Not done. Okay, now we got to add all that stuff to come backwards to size the regulator. Again, that's about the last thing you know. Look at the regulator, do some evaluations. Do I need to put safety reliefs on? Determine your pressure switches. You can help honing in and picking things for there to make things go. Generally sizing your pressure switches to 60 to 80% of the bottom regulated pressure and around 120 on the upper end. That gets you a plus minus 10% flow range in case things are varying. There's some variances, though. You have to take into account your chamber pressures, and not all chamber pressures are constant. You may be running at a -10 all the time, except when you're purging, except when you're light off, except. So you've got to look at all those different scenarios and all the components and all the equipment and do calculations for all the different items that are in there. Okay, so now we've got everything down in there. Run it under different scenarios. What are things going to be happening when you're igniting, when you're operating, when you have turn down, when you have a failure mode? Look at all those different conditions, all those components, make sure you have everything captured, because you're designing for performance, but you have to select every one of those items for safety, because it's really the fuel safety. So we've gone through a lot of quick items that are in here. People got a good feel for it, but there's a lot that we haven't talked about. We haven't talked at all about electrical codes. We haven't talked at all about how to safely wire these things. We haven't talked about ASME B31 codes. What if you need all welded or X-rayed? What if I'm dealing with a toxic gas? Haven't really talked about metering. Haven't talked about elevation effects or special atmospheres. Haven't talked about purging. How do I get the gas into the system? How do I get the gas out of the system? There are a lot of additional effects. That's why I'm only calling this the fundamentals. You get into that second layer, and there's a lot more effects in there. I know a lot of people like to build their own trains and put things together. Bless your hearts, go for it. But there's a lot of subtle things that are in there too. You put the pipe dope on, you ship it, it's all good when it went, but how long is that pipe dope good for? How long until that dries out? What if I'm doing an area where there's seismic shaking and quaking? Is that the right construction? Do I need alternate versions on that? So as burners and combustion systems get more complex, rely on people who specialize in this stuff. We do have a booth. You can ask me more questions out there. But really try and hone in, because it's ultimately safety. Because just because you ship it and you're done it, you've walked off your books, doesn't mean that your liability is ended. Doesn't mean your legal liability is ended. No one wants to be, in front of 12 of their peers to talk about some accidents. So, any questions? All right, I'll let you out early. I won't keep you for another 2.5 hours. All right.